So we left off in lesson 12.1. We were looking at the graphs to interpret limits, and we're going to bring back a really old topic, logistic growth. If you guys remember, this is a formula we used to use back, oh man, it was like December, November maybe. It was a long time ago. So it's gone. It's been pushed out from other information. I gotcha. Well, anyways, here's the formula. We learned it in the logarithm chapter. So the idea was if you have a colony of living items, like there's only so much space and sometimes food that they can grow in. So like we had a deer population question we kept seeing a lot of because at some point the deer they won't be able to thrive beyond a certain point. So when we graph these, they end up looking like this, like Mrs. Hoffbauer did this for us. So they kind of flatten out. So the first one was like, oh, please graph it between 0 and 20. And luckily she already did that for you. So boom, right there. And then it says, use the graph to estimate the number of grams of bacteria present after 8 hours. Well, that was an easy thing for her to do because she already had her function typed in. So she just did a ask command on her calculator's table and then put in 8. And there's approximately 3.736 grams. And then they want us to estimate the limit as time goes on forever. So at some point, this kind of flattens out. And according to your calculator, basically 4 is the threshold. It's not going to be able to hold any more than 4 grams of bacteria, which is, I hope that's good news. I don't know how much bacteria a person needs, but 4 grams seems like a lot. You do need bacteria. So, I'm guessing. I don't know. You pipe down, you. All right, so 15. This is another application that we saw a lot of. We have an exponential decay graph up here, and she already graphed it for you. Thank you, Hoffbauer. And they wanted us to graph it. Thank you, Hoffbauer. And then they want us to estimate after 10 years, so that was an ask thing on our calculator. So the car was worth, remember we talked about cars depreciating in value once unless they're collecting because they're antique, they usually depreciate. So $847.43 after 10 years, and then it says, well, why don't you extend this limit out to forever? What happens to your car value? Well, it's going to flatten out to essentially 0, right? You wouldn't have a car that's worth anything negative. Although I don't know if that's true, because I feel like if you have to have it towed to the junkyard, I feel like it is technically worth negative at that point. But I digress. Let's just pretend you're willing to let it rust out in your front yard. It's worth nothing. And that makes sense, as a human, that makes sense. And as a mathematician, I see that the horizontal asymptote is at y equals 0. So that was the stuff that I forgot to finish. I didn't have time to finish yesterday. So now look at the next lesson, which happens to be our final lesson. No cheers. No cheers? Yay! Woo! It's going to be a good one.
Happy Thursday.
Happy Thursday. All right, so this is my method of choice when it comes to evaluating limits because it's an algebraic approach. And I really don't like having to use my graphing calculator to get graphs. I don't like using tables. I think they're cumbersome, but I am like super good at algebra manipulation, so I like this method the most. All of the ones on your final, I think, unless they're already graphed for you, I feel like this is the way to approach them, but it's going to be up to you guys. If you really love looking at graphs, then go ahead. But we learned yesterday that some of the graphs are a little misleading. Remember our graphs yesterday that looked like lines, but they actually had holes in them? So sometimes you're looking at a graph and you don't realize what you're really looking at, so be careful. So let's talk about functions. Constant functions, you guys okay with me saying a constant function looks like this? It's a horizontal line. Like for instance, f of x equals 2 would be a constant function at 2. The identity function is just a fancy talk for them saying a slanty line, so a line that has a slope, not 0. But remember, this guy can be transformed. The slope could be different than a 1, and you could have a y-intercept different than 0. Okay, there's a lot of red notes here. It says, you will learn these in calc. I'm just going over these to cover the basics, and these are not even all of your properties that you will learn in calc. The good news is, they're kind of intuitive. I know they look really scary, but like they kind of make sense. Or not, I don't know, maybe. For instance, limit of f of x plus g of x is equal to the limit of f of x plus the limit of g of x. Okay, cool. That's nice to know, right? Same thing is true for subtraction. You can put a scalar multiple in or outside of the limit. You could multiply them together, or you could split them apart, as the case may be. Now the division one's a little weird. There's a restriction on here because g of x can't be equal to 0, because we know that would be an undefined issue. The power property is really important. This is like the beginning moment of you understanding a property that will come up again in calculus when you guys start to talk about the next part, which is actually the good part of calc. This beginning part's kind of weird. I think kids get turned off by calculus because of all the weird notation they throw at you in the first few months. So what we need you guys to do when you walk into calculus is to not have any other issues overriding your process. So like, you need to be really good at the basics of math that you guys have been taught for years. So like solving an equation, you should be able to solve that with no mistakes whatsoever. You know, you should be able to, if Mrs. Gupta asks you about trig functions, you know, what's the cosine of pi over 3? You should be able to come up with that real quick, okay? So those are the basic things that apparently are tripping kids up, and it's stopping them from progressing and really understanding like these new properties. This is the point of calculus, okay? So just keep that in mind. She will assign you summer work. You are to do it. I will be checking in with you. It's a warning, isn't it? All right. So let's take a look at this. This is from your textbook. We have a quadratic function, which is a continuous function. Okay. So since this is a quadratic polynomial, it is a continuous function, which means we're not going to have any sort of discontinuities, jumps, holes, anything in it. I mean, it's a quadratic. So when I ask you the limit as x approaches 4, I don't think we need to do anything tricky here, guys. I think we can just plug in x equals 4. So this would be a moment where you would just use direct substitution to evaluate the limit. So that's the first thing I look for. Is it an easy continuous function? If so, plug in the limit number and be done. So here, they're going to warn you that if it's a polynomial, that means it's easy. Direct substitution is the way to go. But if it's a rational function, remember you have restricted values, I think we called them at some point during our school year, where like you can't have x equals 4 because it would give you a divide by 0 in the bottom. So we might have to use some algebra techniques to do some cross-canceling and factoring. So keep that in mind. We'll also talk about, remember, top-heavy, bottom-heavy, and equal weight rational functions. That's going to come back as well when we look at the infinite limits. So here, we're finally on your worksheet, right? Worksheet 2. Example 1. Guys, you have a polynomial, right? This is a quartic with negative coefficients. Doesn't really matter, because I just want you to figure out what happens when x approaches negative 2. Well, I can do you one better. Just tell me what happens when x equals negative 2. So they are going to have you plug it in. Now, did you notice they use parentheses around the negative before they put the exponents on? Yeah, you'd think your pre-calc brains would know to do that, but on our last test I had a few people who did not do that, so keep in mind when you're directly evaluating. You need to use parentheses around things, especially if they're negative with even powers. Spoiler alert, this one comes out to negative 43. So there's no need to graph it, there's no need to use a table and figure out numbers that are close to negative 2. We can just directly substitute in negative 2. So I think we have the same issue going on here, guys. This is a continuous polynomial. And then it says, as x approaches 3, so just plug in a 3. And I know, this being the last lesson, y'all want to impress me with your mental math skills, right? So you're going to do this mentally, but if it was a test, you'd probably use your calculator. I'll try it mentally. Let's see what happens. Oh. Wow, guys, your mental math was so good. All right, number 2. Maybe I'm not sure what this looks like. And you know what, guys? I don't know what it looks like either. So good news. Hotbar graphed it for you. It appears to be continuous. And here's how you know if it's not continuous at 5. Because you'll try plugging in a 5. And if it gives you an error, that means we have a problem. Well, guys, when you plug in a 5 here, you get 5 to the 3rd power minus 4, which is 121. So the square root of 121 is an 11. So that was another direct substitution question. Easy peasy. But what if it's not so easy peasy? What if we have a rational function where I can't just directly substitute in that value? So like for instance, this one here, I cannot plug in an x equals an x equals 1 because in my denominator you get a divide by 0. So what we're going to remember now from last semester is when you have a rational function with polynomials p over q, you might be able to remove the discontinuity if you can factor and cancel. So they didn't do that on that question. Let's look at one that they did do it on. So look at this example here from your textbook. As x approaches -4, well, that's not going to work for direct substitution right now because it's going to give me a divide by 0. But they said, what if you factored that numerator? And then you could cancel the x plus 4 factors. And you're left with just the function x minus 5. So if you remember us graphing rational functions back in this chapter, after you remove the discontinuity, you can graph the remaining polynomial, which in this case is just the line at x minus 5. But there is a hole at, well, let's see, you removed -4, and then do you remember how you find the other factor, or the other part of the coordinate for the hole? You plug it into the remaining piece, yeah. So let's see, -4 minus 5, better known as -9. Now, you don't see that hole here, but it's there, okay? So that's why algebraically we couldn't just directly substitute. But now I could. So the remaining line, if I just pretend it's this line now instead of that rational function, now I can go ahead and evaluate the limit as x goes to -4. So that's what they did over here. So they got, what do you know, -9. It's approaching the hole that we found. Oh, mystery. Okay, so moving on. This one is kind of done for you. Like, is it the same question? It's slightly different? Okay, well that's fun. Alright, so do you guys notice it's already been factored here? They would then cancel the x minus 4s, and you are left with the same polynomial line as the previous example, so that's fun. But this time, they want the limit as x approaches 4. So now you can go ahead and plug in a 4, and you get -1. So if you have a discontinuity and it's the whole or the removable discontinuity kind, you can factor and cancel it out of there. So let's take a look at this one. We're going to have that issue, right? If I plug in a -2, I'm going to have a divide by 0. So a little factoring from you guys. Last day of pre-calc learning. Don't fail me now, guys. How you factor x squared plus 9x plus 14? There you go. So do you see the removable discontinuity now? Remove it. And now you're left with finding the limit as x approaches -2 of x plus 7. I think we can handle that. -2 plus 7, better known as 5. Yes, totally 5. Sometimes. And sometimes 2 is 5. So there we go. Okay, investigate this one with me, guys. Now, I'm looking at it, I'm going, oh, it's something weird, it's irrational, it's a weird thing. I'm sure the graph looks really horrible, but remember, you're supposed to look for the easy way out first. Can't we just directly substitute a -4 here? I mean, yeah. There's nothing wrong with throwing a -4 in here and here. So you're going to end up with a -1/4. And then instead of saying plus -4, I'll just say -4. And then I'm going to really impress my teacher with the ability to get common denominators. Or I'm going to type this in my calculator. What's -1/4 minus 16/4? -17/4? If you're going to use your calculator, could you at least type it right?
I didn't. I was trying to do it in my head.
Oh, see, now you know.
So my brain didn't work, not the calculator.
I'm sorry.
Can't blame my typing abilities.
I shouldn't make you use your brain today. That was cruel.
It was cruel enough.
You know what? I wrote down a decimal in my answer key.
But that's not like you.
That is not like me. Okay, moving on. Number 6. Guys, I'm looking at a polynomial. That is continuous. Could you just please directly substitute? Now be careful. The negative is a coefficient. You are not squaring the negative. 10 minus 4, 6 minus 1 is 5. That was some zippy mental math on my end. I've had a lot of coffee today. Huh? You can't read? Oh my gosh, my poor babies are having such a tough time this last day.
My PS6 proved I can't read.
Oh. You are hilarious. Okay. As x approaches 0, well that, my friends, that's going to be a problem. Are you going to be able to plug in a 0? No. So I'm a stickler for the algebra method. I like to work with the algebra. So look at that first term, that 3 plus x quantity squared term. Can we kind of FOIL that out real quick? Because I think we're going to have some canceling and factoring happening here, I hope. Maybe, maybe not. Let's see. So this guy right here if I expanded that, and I'm going to flip the order around because I hate the order it's in, I'm going to call it x squared plus 6x plus 9. And then remember there's still a, is that a minus 9? I kind of crossed off half of it. I hope it's a minus 9. Okay. Because now, oh, good things are about to happen. I don't know why I wrote Lima. Limit. Limit as x goes to 0. Well, watch this. These are going to be gone. Look at your remaining polynomial in that numerator. That is factorable. Can you take out the x? And, oh my gosh. Okay, you can't read. I can't write.
Together we can fail the SAT.
Oh, you don't need to fail it. That's dramatic. I know. All right, so the x's are gone. You just removed the discontinuity for me. Thank you. So now with the remaining polynomial, which is x plus 6, plug in a 0 for me, and y'all get 6. Very good. So algebra is like my comfy spot in math. Y'all know I can't graph. This is not a mystery. I can't graph, and I have some, like, you know, younger years trauma of not being allowed to use a calculator when I was very young. Algebra 2. So I resorted to really relying on my algebra skills, which is not a bad thing. It's actually kind of an awesome skill to have in college, but so like for me, this is the easiest way for me to do the questions. If you find, you know what, it is not the easiest way for me to do the questions, then you can go back and do the graphing method or the tabling method. Absolutely. Right. All right, let's talk about these infinite limits. So as x goes to positive and negative infinity, which we learned yesterday is essentially just end behavior. Do you guys remember how polynomials work? What? I think you secretly do. Look carefully. If you have a polynomial that has a power that is even, do you guys agree with me that the ends go up, up, or what else could happen? They could go down, down. What would make a polynomial face down, down? If there's a negative lead coefficient. Very good. However, if the power is odd and a positive coefficient is what you have, the right end goes up and the left end goes down. But what would have to occur for it to flip around where it's opposite of that? Same thing, negative lead coefficient. So what I'm going to do, because you know I don't graph well, when I look at the function, I'm going to just draw the ends. And I'm going to just draw two arrows either pointing up, up, down, down, left, up, you know, one of those combinations. And that's how I'm going to determine the end behavior. Which, I hate to break it to you guys, this is how we determined end behavior before this class. So here we go. Let's take a look at some examples. They have a lot of rules about end behavior depending on what your polynomial is. I'm just going to bring back your old topics that you already know about. We don't need to break down the rules today. Okay, we're not interested in that. So, talk about this polynomial with me, guys. This is definitely a polynomial. It's a fifth power with a positive leading coefficient. So what do your ends look like? The left side goes down, the right side goes up. I don't care what happens in between because all I want is as x approaches negative infinity. Well, that means left. So what are you telling me? Now, we know the limit doesn't necessarily exist, but the function is tending towards negative infinity. So you're going to say approaches negative infinity. Oh, yes, it is. Yes. I got confused for a minute too. We were in good company. Okay, so this is from your textbook. I don't think this one's on your notes. Is it? No. So we got to talk about rationals, because rationals are not polynomials, and rationals have different end behavior rules. So the end behavior rules that we learned in rationals, I'm going to kind of simplify it down here. If it is bottom heavy, I know we use that unofficial phrase, bottom heavy, meaning that the polynomial in the denominator is larger degree than the numerator. Do you remember what your horizontal asymptote was? It's at 0. Very good. If it was equal weight, so you had like a quadratic over a quadratic, do you remember how we find the horizontal asymptote? It's the lead coefficients, yeah, and oh, that's not what you're saying? Let's just pretend. So I don't know how to abbreviate this because I don't have any formulas in front of me right now, but basically it's whatever these lead coefficients are. So like if it's something x over something x, it would just be the lead coefficient fraction. So we'll see some examples of this in a minute. And then what if it's top-heavy? That's the oblique one, yeah. So hopefully we don't have to encounter that. It's not the end of the world if you do. It just means it's going to go off to one of the infinities. So we'll discuss that maybe on an upcoming example. Let's take a look at some ones from your notes. Is this on your notes?
Yes.
Where? Oh, it's right there, B. Okay. So you're still in the front of your notes, and I'm looking at this rational function. If I wanted to graph it, I could. And depending on whether I found that interesting or not, I would probably figure out the answer to this question. However, I don't like graphing. So I'm going to look at this rational and determine whether it's top heavy, bottom heavy, or equal weight. That would be equal weight. So because you have an equal weight rational function, your horizontal asymptote on the far ends approaches y equals the lead coefficients. So careful, there's a 1 up here, right? So your lead coefficient would be 1/4. I don't really know if looking at that graph on that graphing calculator would have told me it equals 1/4. I think I would have had to at least trace or use my table. So like for me, I think some of you are as lazy as me. So you just go, what is the quickest way to get this right on my final next week? And in my opinion, looking at the coefficients, the degree weight is the quickest way. So, boom, it's approaching 1/4. This is on the back of your notes now. So now they're going to throw everything kind of together. So you got to be on your toes. We got to say, are we looking at a polynomial? Are we looking at a rational? Because you're going to approach these a little differently. So number 8, this is a poly. It is a third degree poly with a negative coefficient. So what do your end arrows look like? The left side goes upwards and the right side goes downwards. And they are curious about the left end behavior. So you tell me, where's your left end tending towards? It's approaching infinity. Very good. This dude is a rational. So you need to realize whether it's top heavy, bottom heavy, or equal weight. This one is bottom heavy, which means my far end behaviors are going to approach the asymptote at y equals 0. So whether I'm looking at the left side or right side, it doesn't matter. This guy is approaching 0. So we'll just say the limit equals 0. 0 is a number, right? So we can just say it equals 0. The ones that you're not supposed to say like it equals is the infinity ones. We have to say they're approaching infinity or tending towards infinity. Okay, got another rational. Tell me, guys, is this top heavy, bottom heavy, or equal weight? Equal weight. Ooh. That's supposed to say equal. So equal weight says I'm supposed to look at my coefficients for my horizontal asymptote. I would expect better out of you, PreCalc. Don't tell me it's 6/10. It is 6/10, but like PreCalc, that's 3/5. You could even say 0.6. I'd be okay with that. I wouldn't be super excited to see a non... Now, remember, your test next week is in what format? It's multiple choice. No, I didn't actually write this. We can blame Hofbauer for all of it. But, what? Why do you think so evil things of me? All right, so let's talk about this guy. This is a polynomial, a continuous polynomial with a third degree and a positive lead coefficient. So the left side goes down and the right side goes up. And very specifically, they want to know the limit as x goes to negative infinity, so they want to know the left side. So you tell me, where's the left side going? Down. It's approaching negative infinity. Very good. Very good, very good. All right. Is it more of this? Well, how boring. Should I just make you do your homework? We got 11 minutes. I know. Oh, let's look at that medicine question. That one's kind of fun. So, Tamika is taking 2 milligrams of her asthma medicine, and the graph shows the amount of medicine M left in her bloodstream after D number of days. So, find the limit as D approaches 3 on the negative side, so meaning before it hits 3, and then 3 on the plus side, so after it hits 3. So, look at this graph, guys. Here's 3. On the negative side of 3, meaning before it gets to 3, what height are we looking at on this axis about? I know it's not exactly this, but it's close to Yeah, we'll say it's about 2-ish. And then on the right side of 3, this guy here is about 4. So this is a concept where kids have to really kind of think about what's going on in life. And they're like, wait, on day 3, how could she both have 2-ish and also 4-ish milligrams of medicine in her system? So like this is how medicine works, right? Like your body metabolizes it. So the concentration in your bloodstream like decreases as your dosage goes away. And then Tamika must have done what on day 3? Taken a dose at the beginning of the day. So then her bloodstream levels would spike and eventually it trickles off. I think we've all had that moment where your Tylenol stopped working about 2 hours too early and you're like, oh, look at that. So, all right. I'm going to trick you into doing homework. Let's do our homework together right now. Come on, we got this. So, be careful. Some of them are infinite limits and some of them are just like limits at numbers. So the first thing you want to look for if it's just a number is can you just directly substitute? So like check out number 1. Can we just directly substitute? Yeah, we can. All right, so 3 squared plus 3 times 3 minus 8, better known as -8. No?
Okay, so it's 9 plus
Oh,
9.
that's 9. That's
Oh,
not
minus
that.
8 would be 10, right? Because it's going to be 18 minus 8.
I'm just magically creating negative signs where they don't exist is what I'm doing.
Okay.
What is this?
10.
10. Clearly it's 10. I don't know what you crazy people are talking about. Why do I have 28 on my answer key? What did I do? Oh my gosh, I quit.
You took the answer, doubled it, and then added 8.
Sure. That sounds like something I do. I don't know. I give up.
That'll be a fun one.
I'm just, you know what? You don't get answers. You keep it up. All right, number 2. Are you going to be able to directly substitute in a -6 right here? Nah. So we got to do a little fancy factoring maybe? So this numerator, oh, that's nice. That factors into x plus 6 times x minus 6. So now you can remove that discontinuity. And now you can evaluate the limit as x goes to -6 of x minus 6. So let's see if I can get this one right. -6 minus 6 is -12. Wait, what? Oh gosh, don't mess with me, please. It's so fun. I know. All right, number 3. Can we directly substitute in a 4? I think the answer is yeah. So let's see if I get this one right. 16 minus 8 plus 1 is the square root of 9. Oh, I got this. The answer is 3. No, I'm not sure about anything anymore. I really need to finish on a high note, guys. Come on.
How confident are you in that is?
About 95%. Oh. I was confused for a minute. There's more. Okay, let's take a look. Number 4. Number 4. So are you going to be able to directly substitute in a 1? I mean, the answer is probably no, because that doesn't seem like something I would do. So I have a feeling once we factor this denominator, we're going to see that x minus 1 is one of the factors, but I don't know. Let's find out. Maybe you tried plugging in a 1 and it didn't work out for you. So 2x and x. And then let's see. If we had a plus 7 and a minus 1, that is the factorization. So that's why we're not going to be able to directly substitute in a 1, because it would give us a divide by 0 situation. Let's factor this numerator while we're at it. Take out an x. And then now we can remove the discontinuity. So now I'm allowed to go ahead and directly evaluate this limit as x goes to 1 on the remaining x over 2x plus 7. All right, now don't help me this time. That gives me a 1 over 9. Did I get it right? Thank you. I did graduate high school. It was wonderful.
I'm sure your speech just
My speech was fantastic. You would have loved it.
probably, I'm not denying that.
I might be able to find the old cassette recording.
Oh, that would be great.
All right, so if we plug in a 3, now at first kids get nervous on this one because they're like, oh no, right here, 3 minus 3 is 0. But there's more to the denominator there, guys. You're going to have a 2 plus 0. Like, I think that's okay. We can have a 2 in the denominator. So 3 squared, let's see if I got it right this time. That's a 9 over a 2, which is a 9 over 2. So now they're going to switch over to a couple of infinite limits. So these are the end behavior rules. So if it's a polynomial, I want you to think about what the ends look like. And if it's a rational, I want you to think about what the horizontal asymptote would be, because those are end behavior rules. So we have a cubic with a positive coefficient, even though it's at the end there. So your ends look like this. And they, in particular, are asking about the right-hand side, which is right here. So what's that look like? It's approaching infinity. Very good. Nine's boring. Oh wait, I skipped a couple. Oh, 7. Top heavy, bottom heavy are equal weight because we have a rational function this time. Very good. Bottom heavy. And what is the end behavior, the horizontal asymptote on a bottom heavy rational? 0. So if I go either right or left side, doesn't matter. It is approaching. Ooh, that was a weird 0. 0. All right, I'm going to skip around a little bit. Talk to me about number 9. What's your approach, y'all? Just plug it in, yeah. And I think, if I remember correctly from last year, that was a frustrating moment for the teacher, because I had kids who were like really hemming and hawing over a question like this on the final. And I don't know why, because you guys know to plug it in, right? Just plug it in. All right. There's an application question coming up, which means all of you would have skipped it. No, you wouldn't have. Not you. You wouldn't have skipped it. It's about microwaves. So, that's true. Well, this is kind of a silly question. It's the average cost of a microwave manufactured by a company that makes an X number of microwaves for professional kitchens. So, what if they plan on creating 2,000 microwaves? How would you approach this limit? Would you just plug in 2,000? Because I would. I definitely wouldn't be a discontinuity. So the only thing I'm a little concerned about is sometimes you guys forget. If you type everything in one step on your calculator, you have to put parentheses around that. So 250 times 2,000 plus 200,000. Close that quantity before you divide by 2,000. I'm not doing that in my head, you crazy child. I mean, I could, because here the x's cancel, so it's 250 plus 100, so it's 350. Boom!
Very impressive. You redeemed.
See? And that is my final problem of the year. Goodbye.